For billions of years, the Sun has poured unimaginable amounts of energy into the solar system. Its surface burns at thousands of degrees, and its light reaches Earth in just 8 minutes. Yet beyond our planet, space itself remains unimaginably cold. Tonight, Cosmic Bedtime Stories explores one of the strangest mysteries in the universe. Why is space so cold despite the Sun's incredible heat? The answer reveals hidden truths about energy emptiness and the surprising physics that govern the cosmos. Before we begin our journey through the darkness between the stars, please take a moment to like this video and subscribe to Cosmic Bedtime Stories. Every subscription helps bring more relaxing science documentaries to the channel. Now settle in, relax and drift into the fascinating story of why the hottest star in our neighbourhood cannot warm the vast emptiness of space. The outermost structure of space begins in regions so empty that ordinary ideas of temperature lose their familiar meaning. In these vast intergalactic gaps, matter exists only in extremely rare traces, with hydrogen atoms scattered at distances so large that they rarely interact. The universe at this scale is not filled in the way planetary systems or galaxies are filled. Instead, it stretches into near total dilution, where the absence of matter becomes the dominant condition. This emptiness forms the first layer in understanding why space remains cold, even in the presence of intense sources of heat such as stars. In these regions between galaxies, particles drift in isolation. A single hydrogen atom may travel for millions of years without encountering another particle. Without collisions, energy transfer becomes extremely limited. Heat in the physical sense depends on the movement and interaction of particles. When matter is so thinly distributed, there is almost nothing to carry energy from one place to another. As a result, even if radiation passes through these regions, it does not raise the overall thermal state of the sparse gas in any meaningful way. The temperature of such space is often described in relation to the cosmic microwave background, a faint and uniform radiation field that fills the universe. This radiation represents the leftover energy from the early universe and sets a baseline temperature for space itself. In intergalactic regions where no significant structure exists to concentrate heat, this background becomes the most consistent physical influence. The temperature remains only a few degrees above absolute zero, not because heat is absent, but because there is almost nothing present to absorb and store it. Matter in these regions is not entirely absent. It exists as a thin plasma mostly composed of hydrogen and helium, with occasional heavier elements dispersed by ancient galactic processes. These atoms are not bound into molecules or structures. They drift freely, influenced only by weak gravitational fields spread across enormous distances. Without density, there is no mechanism for these particles to build or retain thermal energy. Each atom behaves almost independently, with long periods of isolation separating rare encounters. Radiation passes through this environment without significant obstruction. Photons, the basic units of light, travel across these regions largely unaffected. In denser environments such as planetary atmospheres or stellar interiors, photons interact constantly with matter, transferring energy and creating heat. In intergalactic space, such interactions are minimal. The transparency of this environment means that energy moves through it rather than being absorbed by it. This contributes to the persistent coldness, even though energy itself is present in transit. The structure of this emptiness is shaped by the expansion of the universe. As space expands, matter becomes increasingly diluted across larger volumes. Over billions of years, this process has led to the formation of vast voids between galaxy clusters. These voids are not truly empty, but their density is so low that physical processes associated with temperature become extremely weak. Expansion does not remove energy, but it spreads matter so thin that energy exchange becomes inefficient. In the absence of dense matter, thermodynamic equilibrium is difficult to achieve. Temperature, in a physical sense, reflects the average kinetic energy of particles. In intergalactic space, particles are too widely separated for this average to meaningfully stabilize through interaction. Each particle carries its own energy state, influenced more by distant radiation fields and gravitational history than by local contact. This creates a form of thermal uniformity that is extremely low in value but widespread across space. Despite the coldness, intergalactic space is not static. It contains movement at both large and small scales. Galaxies drift through these regions influenced by gravity from nearby clusters. Within these vast motions, gas is slowly pulled into denser regions where galaxies form and evolve. However, the space between these structures remains largely unchanged in its low-density condition. The energy present in motion does not translate into heat unless it is transferred through collisions or interactions which are rare in this environment. The concept of coldness in these regions is tied not to the absence of energy, but to the absence of matter capable of retaining and redistributing that energy. Radiation may pass through, and particles may carry kinetic energy, but without density there is no collective system to accumulate warmth. The result is a universe where heat exists locally in stars and dense objects, but dissipates rapidly in the vast spaces between them. Over cosmic time, this pattern has remained consistent. As galaxies formed and separated into clusters, the regions between them became more and more sparse. Matter did not disappear, but it became distributed across such enormous distances that interaction rates dropped dramatically. This process established the intergalactic medium as one of the coldest environments in existence, not because it lacks energy, but because it lacks the structure required to transform energy into thermal experience. The first layer of understanding space coldness begins here in this silent and almost featureless expanse. It is a region defined by distant separation and near total isolation of matter. Every physical process that produces warmth on smaller scales becomes ineffective when particles are separated by such vast voids. This establishes the baseline condition from which all inner and more structured regions of space derive their thermal differences. The next layer inward from the deepest cosmic voids brings attention to the faint background radiation that permeates all of space. This radiation forms a nearly uniform field that exists in every direction, regardless of location within the universe. It is extremely weak compared to any local heat source, yet it represents one of the most important physical features of space. Known as the cosmic microwave background, it is the residual energy from an early, much hotter universe that has expanded and cooled over billions of years. Its presence defines a universal thermal flaw that shapes how cold space appears on large scales. This radiation does not behave like heat in a conventional environment. In a dense system, heat is transferred through collisions between particles, gradually raising the kinetic energy of matter. In this case, however, the energy exists primarily in the form of photons traveling freely through space. These photons are extremely low in energy due to the expansion of the universe stretching their wavelengths over time. The stretching process reduces their energy content, lowering their effective temperature to just a few degrees above absolute zero. The uniformity of this radiation is a key feature. It does not concentrate in one region or another, but spreads evenly across the universe. This uniform distribution means that no matter where an observer is located, the background environment of space carries a consistent and weak thermal signal. However, because the intensity is so low, it cannot significantly warm the sparse matter found in intergalactic regions. Instead, it acts as a faint and constant reminder of the universe's earlier hotter state. Interaction between this radiation and matter is minimal. In regions where particles are sparse, such as intergalactic space photons, can travel for vast distances without being absorbed. When absorption does occur, the energy transfer is extremely limited due to the low density of matter. As a result, the radiation does not accumulate into heat in the way sunlight warms a planetary surface. The lack of repeated interactions prevents energy from building up in any localized region. The origin of this radiation lies in the early universe, when matter and radiation were tightly coupled in a hot, dense plasma. At that stage, particles and photons interacted constantly, maintaining thermal equilibrium. As the universe expanded and cooled, matter and radiation decoupled, allowing photons to travel freely for the first time. This moment created a snapshot of the early thermal state of the universe, preserved as a fading background that continues to cool as space expands. Expansion plays a critical role in shaping the temperature of this radiation. As space itself stretches, the wavelength of each photon increases. Longer wavelengths correspond to lower energy levels, which results in a gradual cooling effect across cosmic time. This process continues today, meaning the background radiation is slowly becoming even colder as the universe evolves. Despite this, it remains detectable and measurable, forming a persistent layer of energy that fills all of space. In relation to the coldness of space, this radiation establishes a baseline that prevents temperatures from reaching absolute zero. Even in the most isolated regions, where matter is almost entirely absent, this faint radiation still exists. However, because it interacts so weakly with sparse matter, it does not significantly alter the thermal conditions of intergalactic space. Instead, it defines a minimal energy environment that is uniform but extremely low in intensity. The presence of this background also highlights the difference between energy and temperature. Energy exists in many forms, including radiation, motion, and fields, but temperature depends on how that energy is distributed among particles. In regions with almost no matter, energy cannot be efficiently converted into thermal motion. As a result, even though radiation fills space, it does not translate into warmth in any meaningful way. The cosmic microwave background also interacts subtly with larger structures. When it encounters galaxies or clusters, a small fraction of its photons can be scattered or absorbed, contributing minimally to local energy budgets. However, these interactions are negligible compared to energy produced by stars or other active astrophysical processes. The radiation remains mostly unchanged as it travels through space, maintaining its uniform appearance across the observable universe. This layer of space reveals that coldness is not simply the absence of energy, but the presence of energy that cannot be effectively used. The radiation exists everywhere, yet it carries so little power that it cannot overcome the emptiness of intergalactic regions. The result is a universe filled with faint energy that remains thermally insignificant on large scales. Over time, as the universe continues to expand, this background radiation will become even more diffuse and colder. Its wavelength will stretch further, and its energy will diminish accordingly. This ongoing process ensures that the baseline temperature of space will continue to decline, reinforcing the deep cold that characterizes the cosmos. In this second layer, space is not defined by emptiness alone, but by the presence of a universal fading glow that permeates all regions. It is a silent and uniform structure that connects every part of the universe, yet it remains too weak to overcome the extreme dilution of matter. This combination of weak radiation and near absence of particles is a key reason why space remains profoundly cold, even in the presence of a universe filled with energetic sources. Between the vast voids of intergalactic space and the faint background radiation that fills the universe, there exists a subtle medium composed of extremely diffuse gas. This intergalactic gas forms a thin network of hydrogen and helium that stretches across enormous distances, connecting galaxies in a barely perceptible structure. Although it is far more substantial than a perfect vacuum, it remains so rarefied that its physical behavior is dominated by isolation rather than interaction. In this layer, the question of why space remains cold becomes closely tied to the scarcity of collisions and the weakness of energy transfer. The atoms in this medium are separated by distances so large that direct contact is extraordinarily rare. A single particle may drift for millions of years without encountering another. In such conditions, temperature becomes a limited concept, because temperature depends on frequent interactions that distribute energy evenly among particles. Without those interactions, each atom retains its own energy state, with little influence from its surroundings. The result is a medium that exists physically but behaves thermally, as if it is almost disconnected from itself. Most of this gas is composed of hydrogen, the simplest and most abundant element in the universe. Some helium is present as well, along with traces of heavier elements that have been dispersed by ancient stellar processes. These atoms are not arranged into clouds or structures in most regions. Instead, they form a thin and uneven distribution that reflects the large-scale shape of cosmic expansion and gravitational influence. Even where density slightly increases, it remains far below the conditions required for efficient heat exchange. Radiation passing through this medium interacts only occasionally with its particles. When a photon encounters an atom, it may transfer a small amount of energy, but such events are extremely infrequent. The vast majority of radiation travels through unaffected, continuing its journey across the universe. This lack of interaction prevents the gas from reaching higher thermal states, even when exposed to energetic sources such as distant galaxies or quasars. Energy flows through the medium rather than being absorbed and stored within it. In regions where the gas density is slightly higher, small thermal variations can occur. These variations are often linked to gravitational effects that slowly compress the gas, increasing the likelihood of collisions. However, even in these relatively denser regions, the overall temperature remains low compared to astrophysical standards. The absence of sustained energy input means that any localized heating is weak and transient, unable to overcome the cooling effect of expansion and isolation. The expansion of the universe continues to stretch this gas over time. As space expands, the density of particles decreases further, making interactions even less frequent. This gradual dilution reinforces the cold nature of the intergalactic medium. Unlike systems where compression increases temperature, the large-scale expansion of the universe tends to spread energy and matter so thinly that thermal equilibrium remains at extremely low levels. Despite its thinness, this medium plays an important role in cosmic structure. It acts as the reservoir from which galaxies draw material and into which they expel energy through stellar winds and explosive events. However, these exchanges occur over long timescales and across vast distances. The energy injected into the medium by such processes is quickly dispersed and diluted, preventing the buildup of heat in any localized region. Instead, it becomes part of the broader, slowly evolving thermal background of space. The relationship between density and temperature in this environment is not intuitive in everyday terms. On Earth, higher energy often leads to higher temperature because particles are confined and interact frequently. In intergalactic gas, however, energy can exist without significantly affecting temperature if interactions are too rare. Photons and particles may carry energy, but without a medium dense enough to distribute it, that energy does not translate into sustained warmth. The structure of this gas also reflects the gravitational influence of nearby galaxies and clusters. In some regions, it is gently pulled into filaments that connect large-scale cosmic structures. These filaments are slightly denser than surrounding voids, yet still extremely cold by conventional standards. Even within these structures, the same principle applies. Insufficient particle interaction leads to minimal thermal buildup. Over time, this gas gradually participates in cosmic cycles. Some of it is drawn into galaxies where it becomes part of star formation processes. The rest remains in intergalactic space, slowly evolving under the influence of expansion and gravity. Throughout these processes, the fundamental condition remains unchanged. The gas is too diffuse to efficiently convert energy into heat. This layer of space demonstrates that coldness arises not only from distance or emptiness, but from the fundamental limitation of interaction itself. Even when matter is present, it must be sufficiently concentrated to allow energy exchange. Without that concentration, the universe remains thermally inactive on large scales, maintaining its deep and persistent cold state, despite the presence of matter and radiation throughout its structure. Within the large-scale structure of the universe, matter is not evenly spread, but gathered into vast clusters of galaxies surrounded by enormous regions of sparse gas. These galaxy clusters contain some of the most massive gravitationally bound systems known, where hundreds or even thousands of galaxies are held together by gravity. Yet even in these dense cosmic environments, much of the volume remains filled with extremely thin plasma. This hot but rarefied material forms a crucial transition layer in understanding why space can contain intense energy sources while still remaining overwhelmingly cold. The gas within galaxy clusters is often heated to extremely high temperatures through gravitational compression. As matter falls into the deep gravitational wells created by dark matter and galaxies, it accelerates and converts kinetic energy into thermal energy. This process raises the temperature of the plasma to millions of degrees. Despite this extreme heat at the particle level, the gas remains very low in density. The particles are so widely separated that collisions are infrequent compared to dense environments such as stellar interiors or planetary atmospheres. This separation between temperature and density is central to the thermal nature of space. Although the particles in cluster plasma carry high energy, the total amount of matter present is small. Heat in the physical sense depends not only on the energy per particle, but also on how effectively that energy is shared and stored within a system. In these conditions, energy is distributed across such a large volume that it does not translate into a warm environment in the conventional sense. Radiation plays a major role in how this hot gas loses energy. At such high temperatures, the plasma emits X-rays, a form of high-energy electromagnetic radiation. This emission allows the gas to slowly cool over time, even though the cooling process can take billions of years. The radiation escapes into space without significantly heating surrounding regions, because the density of nearby matter is too low to absorb it efficiently. As a result, energy is continuously radiated away into the broader universe. Despite the extreme temperatures within the gas itself, the experience of surrounding space remains cold, because there is no medium dense enough to transfer that heat outward effectively. The energy is confined to the particles that hold it, and without frequent interactions, it does not spread into the surrounding environment. This creates a paradoxical situation where regions of extremely hot plasma exist within a universe that is on average very cold. The structure of galaxy clusters is shaped largely by dark matter, an invisible form of mass that interacts through gravity but not through light or electromagnetic forces. Dark matter forms the scaffolding around which ordinary matter accumulates. It deepens gravitational wells, drawing in gas and galaxies. However, because it does not interact thermally, it does not contribute directly to heating or cooling processes. Its presence influences structure, but not temperature in the traditional sense. Between galaxies within a cluster, vast regions of space remain nearly empty. Even though these clusters contain large amounts of matter compared to intergalactic voids, the density within the space between galaxies is still extremely low. This means that most of the volume inside a cluster is effectively cold despite the presence of localized hot plasma. The overall impression of temperature in space is therefore dominated by emptiness rather than energetic regions. Energy transfer within these clusters is slow and inefficient on cosmic scales. When galaxies interact or pass through dense gas, they may generate shock waves that briefly heat the surrounding plasma. However, these effects are localized and do not significantly alter the thermal state of the cluster as a whole. The energy is quickly dispersed and radiated away, returning the environment to its long-term low-density equilibrium. The behavior of matter in this layer shows that heat alone does not define environmental warmth. A system can contain extremely energetic particles while still existing in a state that feels cold on large scales if there is insufficient material to carry and distribute that energy. This distinction becomes especially clear in galaxy clusters, where the most energetic gas in the universe coexists with vast regions of near-empty space. Over time, the hot plasma within clusters continues to evolve. Some of it cools and condenses, potentially contributing to new star formation in galaxies. The rest remains in a diffuse state, gradually losing energy through radiation. This long-term process slowly reduces the thermal energy available in the cluster environment, reinforcing the dominance of cold conditions on larger scales. In this fourth layer, the universe reveals a key principle. Extreme heat does not necessarily overcome cosmic coldness when matter is sparse. Instead, temperature and perceived warmth depend on density interaction and the ability of energy to spread through a medium. Even the hottest known gas in space exists within a framework that prevents it from transforming the surrounding universe into a warm environment. Surrounding galaxy clusters and extending outward into the broader structure of the universe, a faint and extended region of matter forms what is often described as the galactic halo environment. This halo is not a solid boundary, but a diffuse sphere of gas-dark matter and scattered particles that envelops each galaxy and galaxy group. It represents a transitional zone between the dense interior of galaxies and the nearly empty intergalactic voids beyond. In this region, the conditions that determine temperature become even more dependent on isolation and weak interaction. The gas within galactic halos is extremely thin, composed primarily of hydrogen, that has been stripped of electrons and exists as a weak plasma. This material is held loosely by the gravitational influence of the galaxy, extending far beyond the visible stellar disk. Although it spans enormous distances, the density is so low that collisions between particles are rare events. Each atom or ion moves through space with long intervals of isolation, limiting the transfer of energy between them. Because temperature depends on frequent particle interactions, the halo environment behaves thermally in a highly inefficient manner. Even when individual particles carry significant energy, they cannot easily share that energy with surrounding matter. As a result, the gas does not develop a uniform or strongly defined thermal state. Instead, it exists in a loosely connected distribution, where energy is unevenly spread and slow to equilibrate. Radiation passing through the halo encounters only sparse material. Photons emitted from stars' supernova remnants or distant galaxies may pass through this region with minimal absorption. Occasional interactions occur, but they are not frequent enough to meaningfully alter the thermal structure of the gas. This transparency allows energy to escape the galaxy without significantly heating the surrounding halo, reinforcing the overall coldness of the larger environment. Dark matter dominates the mass of the halo, although it does not interact with radiation or ordinary matter except through gravity. It forms an invisible structure that shapes the distribution of gas and influences the motion of stars and satellite galaxies. Despite its gravitational importance, It does not contribute directly to temperature or heat transfer. Its presence determines structure rather than thermal behavior, leaving the gas dynamics to be governed entirely by rare collisions and weak radiation effects. In some regions of the halo gas may be slowly accreted toward the central galaxy. As it falls inward, it can gain energy through gravitational acceleration, leading to mild heating upon compression. However, this heating is limited by the overall low density. Even when energy increases locally, it does not result in sustained warmth across the halo. The energy is quickly redistributed or radiated away, preventing long-term thermal accumulation. The outer portions of the halo merge gradually with the intergalactic medium. This transition is not abrupt but smooth, reflecting the continuous decline in matter density with distance from the galaxy. As particles become even more widely separated, interactions diminish further, and the thermal state approaches that of the surrounding cosmic voids. This gradient reinforces the idea that coldness in space is not confined to empty regions, but extends through multiple layers of increasingly diffuse matter. Energetic events within galaxies such as supernovae or active galactic nuclei can inject large amounts of energy into the halo. These processes can heat localized regions and drive outflows of gas. However, the energy carried by these outflows disperses quickly as they expand into lower density space. Without sufficient matter to contain and transfer this energy, the heating effects fade over time, leaving behind an extended but still cold halo structure. The motion of particles within the halo is governed primarily by gravity rather than thermal pressure. This means that kinetic energy does not translate efficiently into sustained heat. Particles may move rapidly under gravitational influence, but without frequent collisions, their energy remains largely unshared. This separation between motion and temperature is a defining feature of this region. Over long timescales, the galactic halo acts as both a reservoir and a conduit for matter exchange. Gas is slowly drawn into galaxies, while other material is expelled outward through energetic processes. Despite this exchange, the overall thermal state remains low-shaped by the persistent lack of density and interaction. The halo does not accumulate heat in a lasting way, even though it participates actively in galactic evolution. This layer of space demonstrates that even in regions influenced by massive galaxies, coldness persists, due to the same fundamental principle seen in deeper cosmic layers. Energy requires interaction to become heat. Without sufficient particle density, energy remains isolated and transient, unable to transform the environment into a warm system. The galactic halo thus serves as a bridge between structured galaxies and the cold emptiness of intergalactic space, maintaining the universe's overall thermal quietness. Inside the boundaries of a galaxy, the environment becomes more structured yet still remains dominated by vast regions of emptiness. The Milky Way interstellar medium fills the space between stars with a mixture of gas dust and charged particles. This medium is far denser than the intergalactic environment, but still extremely thin compared to any atmosphere or liquid system. It forms a complex internal layer where matter is present in greater amounts, yet still too sparse to efficiently sustain large-scale heat distribution. The interstellar medium is composed mainly of hydrogen in both atomic and molecular forms, along with helium and trace heavier elements produced by previous generations of stars. These materials are not evenly distributed. Instead, they exist in a patchwork of regions with varying density and temperature. Some areas are warm and ionized, while others are cold and neutral. Despite these variations, the overall average remains low in density, limiting the frequency of particle collisions that would normally drive thermal equilibrium. In this environment, temperature is strongly influenced by local conditions rather than a uniform background. Regions near energetic stars can be heated by intense radiation, causing atoms to lose electrons and form plasma. In contrast, shielded regions far from stellar influence can remain extremely cold, allowing molecules to form and persist. This contrast creates a dynamic but thermally fragmented medium where energy does not spread evenly across space. Radiation from stars plays a central role in shaping the thermal structure of the interstellar medium. Ultraviolet light can ionize gas, while infrared radiation can be emitted as dust absorbs and re-emits energy. However, because the medium is so thin, much of this radiation travels long distances without being fully absorbed. Energy moves through the galaxy in a largely open system, with only partial transfer to surrounding matter. Dust grains within the interstellar medium contribute to localized cooling processes. These small solid particles can absorb radiation and re-emit it at longer wavelengths, redistributing energy in subtle ways. However, their overall abundance is low, and they cannot significantly alter the large-scale thermal balance of the galaxy. Their influence remains important for specific processes such as star formation, but not for raising the overall temperature of space. The presence of cold molecular clouds is one of the most significant features of the interstellar medium. These clouds are dense compared to surrounding gas but remain extremely cold, often only a few tens of degrees above absolute zero. Their low temperature results from efficient shielding from external radiation combined with slow internal energy exchange. Within these clouds, gravity can slowly gather matter, eventually leading to the formation of new stars. Yet even here, the environment remains predominantly cold until collapse begins. Between these denser structures, vast regions of more diffuse gas exist, where particles are so widely separated that collisions become infrequent again. These regions resemble the conditions of intergalactic space on a smaller scale. The result is a galaxy filled with alternating zones of relative density and near-empty space, but with no continuous medium capable of sustaining uniform warmth. Supernova explosions inject energy into the interstellar medium, creating shock waves that compress and heat surrounding gas. These events temporarily raise local temperatures to extremely high levels. However, the energy quickly disperses into surrounding low-density regions and the heated gas expands and cools. The overall effect is transient with no long-term increase in average temperature across the galaxy. Magnetic fields permeate the interstellar medium, guiding the motion of charged particles and influencing the structure of gas clouds. While they affect movement and distribution, they do not directly contribute to heat in the traditional sense. Their presence organizes matter but does not increase the efficiency of energy transfer between particles. Despite the variety of energetic processes occurring within galaxies, the interstellar medium remains largely cold when considered on a broad scale. The reason lies in the persistent low density of matter, which limits the frequency and effectiveness of energy exchange. Even in regions influenced by strong radiation or shock waves, the system as a whole cannot retain heat in a sustained manner. This internal galactic environment demonstrates that the presence of energy sources does not guarantee warmth. Instead, warmth depends on the ability of matter to absorb, store, and redistribute energy through frequent interactions. In the interstellar medium, this requirement is only partially met, resulting in a galaxy that contains both extreme heat and extreme cold, often separated by relatively small spatial scales. Over long periods, the interstellar medium evolves as material cycles through stars, clouds, and diffuse regions. Gas is continuously recycled, heated, cooled, and redistributed by stellar activity. Yet throughout this cycle, the fundamental limitation remains unchanged. The medium is too sparse to achieve uniform thermal conditions, allowing cold regions to persist even within an active and energetic galaxy. Within the colder and denser portions of the interstellar medium, Molecular clouds form regions where gas and dust gather into large, slow-moving structures. These clouds are the primary sites of star formation, yet they begin in conditions that are among the coldest within a galaxy. Despite containing significant amounts of matter compared to surrounding space, they remain extremely diffuse by everyday standards. Their internal temperature is low because energy transfer is limited and radiation is partially blocked by dust. Molecular clouds are composed mainly of hydrogen molecules along with helium and trace heavier elements. The presence of dust grains plays an important role in their structure. These grains absorb and scatter incoming radiation, reducing the amount of external energy that penetrates deep into the cloud. This shielding effect allows the interior to cool more effectively than surrounding regions, enabling temperatures to drop to only a few tens of degrees above absolute zero. In this environment, thermal motion becomes slow, and chemical reactions proceed at a very gradual pace. The coldness of these clouds is not due to the absence of energy in the universe, but due to the limited pathways available for energy to enter and circulate within them. Radiation from nearby stars is weakened as it passes through outer layers, and the dense dust further reduces energy transfer. Without frequent collisions driven by external heating particles inside the cloud, lose energy over time through radiation gradually settling into a low-energy state. Despite their cold nature, molecular clouds are not static. Gravity acts continuously on the material within them, slowly drawing particles together. As regions of slightly higher density form, they begin to attract more gas, increasing their mass over time. However, this process is extremely slow and occurs over long timescales. The cloud remains cold during most of its evolution, with gravitational energy gradually accumulating, but not yet converting into significant heat. Within these clouds, turbulence plays a subtle role in shaping structure. Gas moves in complex slow flows driven by past energetic events, such as supernova shock waves or galactic rotation. These motions can create variations in density and temperature, but they do not significantly raise the overall thermal state. Instead, they contribute to the formation of filaments and clumps, where future stars may eventually form. Magnetic fields thread through molecular clouds, influencing the movement of charged particles and providing partial support against gravitational collapse. These fields do not generate heat directly, but they affect how energy is distributed within the cloud. In some regions, magnetic tension can slow down the collapse of material, maintaining cold, diffuse conditions for longer periods. Radiation within molecular clouds behaves differently than in more open regions of space. Photons are frequently absorbed and re-emitted by dust, leading to a gradual reduction in energy intensity as radiation penetrates deeper into the cloud. This process allows the interior to remain shielded from external heating sources, reinforcing the cold environment. However, because the medium is still not dense enough for efficient thermal conduction, the energy that does enter does not spread uniformly. As density increases in localized regions, gravitational contraction begins to play a more dominant role. When gas is pulled inward, it compresses and slowly heats up. However, this heating remains localized and is balanced by the cloud's ability to radiate energy away. Only when collapse reaches a critical threshold does temperature rise significantly enough to initiate star formation. Until that point, cold conditions dominate the structure. The balance between cooling and gravitational heating defines the evolutionary path of molecular clouds. Cooling processes driven by radiation emission and low-density interactions keep the cloud cold for extended periods. Gravitational processes gradually build energy within localized regions, but they do not immediately overcome the overall thermal state of the cloud. Even within these dense regions of a galaxy, the broader principle remains consistent with all previous layers of space. Low interaction rates lead to persistent coldness. Energy may be present in the form of radiation motion or gravitational potential, but without sufficient collisions and absorption, it cannot establish a warm environment on large scales. Molecular clouds therefore represent a key transitional environment in the universe. They are cold enough to preserve fragile molecular structures, yet dynamic enough to eventually form stars. Their existence shows that coldness is not a lack of activity, but a condition where energy is present but restrained by limited interaction and slow transfer. Within a galaxy, the region occupied by planets, debris, and sparse gas between them forms the interplanetary medium of a solar system. In the case of a system like the one surrounding the Sun, this medium is far thinner than any planetary atmosphere, yet it is not completely empty. It contains charged particles, dust grains, and faint traces of neutral gas that extend outward from the star. Despite being closer to a powerful heat source than almost any other region in space, this environment remains overwhelmingly cold in practical terms due to extreme dilution of matter. The dominant component of the interplanetary medium is the solar wind, a continuous outflow of charged particles emitted from the outer layers of the Sun. These particles travel outward in all directions, carrying energy and magnetic fields across the solar system. Near the Sun, the solar wind is relatively dense and energetic, but as it expands outward, it spreads across a growing volume of space. This expansion causes the density to decrease rapidly, weakening the ability of particles to interact and exchange energy. Temperature in this region can be high when measured as the average kinetic energy of individual particles. However, this does not translate into warmth in the conventional sense. The reason lies in the extreme scarcity of matter. Even when particles move rapidly, they are so widely separated that collisions are rare. Without collisions, energy cannot be efficiently shared or converted into heat within a surrounding environment. As a result, the interplanetary medium remains effectively cold despite containing energetic particles. Dust grains within this region are remnants of comets, asteroids, and interstellar material. These particles are small and widely dispersed. They can absorb sunlight and re-emit energy in infrared wavelengths, but their overall contribution to heating the surrounding space is minimal. The vast distances between grains prevent them from forming a connected thermal system. Each grain behaves almost independently, interacting more with radiation than with other particles. Radiation from the Sun is the primary source of energy within this region. Sunlight carries immense energy, and near planetary bodies it can produce significant heating effects. However, in the interplanetary medium itself, there is little matter to absorb this energy. Photons travel freely across space, only occasionally interacting with particles. This means that most of the solar energy passes through the region without being converted into local thermal energy. As distance from the Sun increases, the intensity of radiation decreases according to geometric spreading. Energy spreads over larger and larger spherical surfaces, reducing its density. This weakening effect contributes to the cooling nature of outer regions of the solar system. Even though energy is still present, its distribution becomes too thin to maintain significant heating effects on sparse matter. The heliosphere defines the boundary of the Sun's influence, where the solar wind interacts with interstellar space. Within this region, solar particles dominate the environment, but beyond it, interstellar particles become more significant. The transition is gradual rather than abrupt. In both regions, however, the fundamental limitation remains the same: low particle density prevents efficient thermal coupling. Energetic events such as solar flares and coronal mass ejections can temporarily increase the energy content of the interplanetary medium. These events send bursts of charged particles outward, increasing local density and energy levels. However, as these bursts expand, they also thin out and lose their ability to maintain concentrated heat. The energy disperses over vast distances, returning the medium to its typical low-density state. Magnetic fields carried by the solar wind shape the structure of the interplanetary medium. These fields influence the motion of charged particles, creating large-scale patterns and boundaries. While they affect particle trajectories, they do not directly contribute to heat in a traditional sense. Their role is structural rather than thermal, guiding the flow of energy without increasing its concentration. The interplanetary medium illustrates a key principle. Proximity to a strong energy source does not guarantee warmth if matter is too sparse to absorb and retain that energy. Even near a star capable of producing enormous heat, the surrounding space remains cold because energy is not efficiently stored in the absence of dense material. Over time, the solar wind continues to shape the environment of the solar system, constantly streaming outward and interacting with interstellar space. Yet despite this continuous flow of energy, the interplanetary region remains dominated by emptiness. The combination of expanding particles, weak interactions, and low density ensures that heat does not accumulate, preserving the cold character of space even within the reach of a star. At the boundary where the sun's influence begins to weaken significantly, the heliosphere forms a vast protective bubble filled with solar wind and magnetic fields. This region extends far beyond the orbits of the outer planets and represents a transitional environment between stellar and interstellar space. Within it, charged particles from the sun still dominate the local conditions, yet their density steadily declines as they move outward. This gradual thinning is central to understanding why space remains cold even in the presence of continuous solar energy output. The solar wind originates from the sun's outer atmosphere, where high temperatures allow particles to escape the sun's gravitational pull. These particles stream outward at high speeds, carrying energy, momentum, and magnetic fields across the solar system. Near the sun, this flow is dense enough to influence planetary environments significantly. However, as it expands into the heliosphere, it spreads across an increasingly large volume, causing a rapid drop in particle density. Temperature within the solar wind refers to the kinetic energy of individual particles rather than the heat of a surrounding medium. Although these particles move at extremely high speeds, they are separated by large distances. This separation limits the frequency of collisions which are necessary for transferring energy into a shared thermal state. As a result, the solar wind can be hot in a particle sense, while still existing in an environment that does not feel warm or thermally active in the conventional sense. The heliosphere contains regions of varying density and structure. Closer to the sun, the solar wind is more continuous, while farther out it becomes more turbulent and irregular. These variations are influenced by solar activity cycles, including periods of increased or decreased particle emission. However, regardless of these fluctuations, the overall trend is consistent. Expansion leads to dilution, and dilution leads to reduced thermal interaction. As the solar wind travels outward, it eventually encounters the interstellar medium. This boundary region is known as the heliopause, where the outward pressure of solar particles balances the incoming pressure of interstellar particles. At this interface, complex interactions occur, including shock waves and particle deflections. Despite these energetic processes, the region remains extremely thin in terms of matter density. Energy exchange occurs, but it is spread across such vast distances that it does not create a warm environment. Beyond the heliopause lies interstellar space, where particles from the sun become increasingly rare. The transition is not marked by a sharp boundary, but by a gradual blending of solar and interstellar materials. In this outer region, the influence of the sun weakens and the conditions of the galaxy begin to dominate. Even so, both regions share a common characteristic: extremely low density prevents efficient heat transfer. Dust and charged particles within the heliosphere also contribute to its structure. These particles originate from comets, asteroids, and interstellar sources, and they interact weakly with solar radiation. While they can absorb and re-emit energy, their contribution to overall heating is minimal due to their scarcity. Each particle behaves largely independently, with little opportunity for collective thermal behavior to emerge. Magnetic fields carried by the solar wind extend throughout the heliosphere, forming a complex structure known as the interplanetary magnetic field. These fields guide charged particles along curved paths and influence the shape of large-scale regions. However, magnetic fields themselves do not directly produce heat. Instead, they affect how particles move and distribute energy without significantly increasing thermal density. Occasionally, bursts of solar activity such as coronal mass ejections disrupt the heliosphere. These events inject large amounts of energetic particles into space, temporarily increasing density and energy levels in localized regions. Yet even these dramatic events do not overcome the fundamental limitation of space expansion into vast volume quickly disperses energy, preventing long-term thermal accumulation. The heliosphere demonstrates that even within a structure dominated by a star, space remains overwhelmingly cold. Energy is continuously emitted, yet it is distributed over such large distances that it cannot create sustained warmth in the surrounding environment. The key limiting factor is not the absence of energy, but the inability of matter to concentrate and retain it through frequent interactions. As the solar system moves through the galaxy, the heliosphere itself shifts through different interstellar environments. These changes can subtly alter its shape and size, but they do not change the underlying thermal behavior. The environment remains defined by low-density plasma and weak particle interaction, ensuring that the overall system stays cold on a macroscopic scale. This outer boundary layer of stellar influence reinforces a consistent pattern seen throughout space. Whether in intergalactic voids, galaxy clusters, or stellar neighborhoods, this same principle applies. Without sufficient matter, density energy cannot be effectively transformed into heat. Even the most powerful continuous outflow of stellar energy becomes diffuse and thermally ineffective when spread across the vastness of space. Closer to the center of a planetary system, the region of near-Earth orbit introduces a significantly different balance between radiation matter and temperature perception. At this altitude, Earth's atmosphere becomes extremely thin, gradually fading into the vacuum of space. This transition zone contains a sparse mixture of neutral atoms, ionized particles, and trace gases that extend far above the surface. Although it is still influenced by a planet capable of supporting life and complex climate systems, the environment here is defined more by near-vacuum conditions than by atmospheric warmth. In low Earth orbit, the density of matter is so low that collisions between particles are rare compared to those in lower atmospheric layers. Without frequent collisions, energy cannot be efficiently shared or converted into a uniform thermal state. As a result, temperature becomes a less intuitive concept. Individual particles may carry significant energy, but the absence of dense matter prevents that energy from manifesting as a continuous warm environment. This region is exposed directly to solar radiation. Sunlight arrives without the filtering effects of dense atmospheric layers, delivering intense energy to any exposed surface. However, the surrounding space itself does not retain this energy. Photons travel freely through the region, interacting only occasionally with sparse particles. The lack of absorption means that most of the solar energy continues its journey without being converted into heat within the surrounding environment. When objects are present in this region, they experience extreme variations in energy exposure. Surfaces exposed to sunlight can heat rapidly, while those in shadow cool quickly by radiating energy into space. This rapid fluctuation reflects the absence of a medium capable of distributing heat evenly. In a dense atmosphere, energy spreads through collisions and convection. In near-Earth orbit, these processes are absent, leaving radiation as the only significant mode of energy transfer. The upper atmosphere, particularly the thermosphere, exhibits a counterintuitive relationship between temperature and heat content. Particles in this layer can reach extremely high kinetic energies due to absorption of solar radiation, yet the overall density is so low that the total heat content remains minimal. This means that although individual particles are energetic, they cannot collectively warm the environment in a way that resembles conditions near the surface of a planet. Ionized particles in this region form a weak plasma influenced by Earth's magnetic field. These particles move along magnetic field lines, creating structures such as the auroral zones near the poles. While these interactions produce visible light phenomena, they do not significantly increase the thermal energy of the surrounding space. The energy involved is highly localized and does not translate into widespread heating. The transition from atmosphere to space is gradual rather than abrupt. As altitude increases, air density decreases exponentially. This means that each successive layer contains fewer particles capable of carrying and distributing heat. Eventually, the environment becomes so thin that it behaves more like space than like an atmosphere, even though it is still gravitationally bound to Earth. Radiation dominates energy transfer in this region. Without sufficient matter for conduction or convection, electromagnetic radiation becomes the primary mechanism through which energy moves. This allows heat to be absorbed and emitted by individual particles or objects, but prevents the formation of a uniform thermal environment. The result is a system where energy exists but remains unevenly distributed. Microscopic dust particles and atomic remnants also exist in this region, often originating from meteoroid ablation or atmospheric escape processes. These particles are widely scattered and do not form stable interactions with one another. Their contribution to thermal dynamics is minimal, reinforcing the overall cold and thin nature of the environment, despite its proximity to a planetary heat source. Even though Earth itself radiates heat and receives continuous solar energy, the surrounding near-orbital space remains cold because there is no dense medium to store or distribute that energy. Heat does not accumulate in the vacuum. It passes through or remains confined to isolated objects. This separation between energy sources and energy retention defines the thermal character of this region. The presence of a strong gravitational field does not alter this fundamental limitation. Gravity holds the atmosphere close to the planet, but does not increase particle density in the upper layers enough to support efficient thermal exchange. As a result, the boundary between atmosphere and space remains a region where cold conditions dominate despite proximity to a warm planetary surface. This layer demonstrates that even near a planet capable of sustaining life and stable temperatures, space itself remains cold due to the absence of sufficient matter. Energy is abundant, but without a medium dense enough to distribute it, that energy does not translate into warmth in the surrounding environment. Above the thin edge of Earth's upper atmosphere, the thermosphere forms a region where energy from the sun interacts directly with extremely sparse particles. Despite being part of a planet's extended atmospheric envelope, this layer behaves more like space than a traditional atmosphere. The density of gas here is so low that collisions between particles are rare, and energy transfer occurs in a highly limited and uneven manner. This creates a situation where temperature rises in theory, yet heat content remains extremely small in practice. Solar radiation is the primary driver of energy in this region. High-energy ultraviolet and X-ray photons from the sun strike atomic oxygen and nitrogen, stripping electrons and creating ionized particles. This process increases the kinetic energy of individual particles significantly. However, because the number of particles is extremely small, the total amount of energy stored in the region is minimal compared to denser atmospheric layers below. The environment can therefore reach very high measured temperatures while still feeling like a near vacuum. The concept of temperature in this layer becomes increasingly abstract. In dense matter, temperature reflects the average motion of a large number of interacting particles. In the thermosphere, interactions are so infrequent that each particle behaves almost independently. A single energetic particle may carry substantial energy, but it cannot easily transfer that energy to its surroundings. As a result, thermal equilibrium is not fully established across the region. Ionization plays a central role in shaping the behavior of this layer. When atoms lose electrons, they become charged and respond strongly to Earth's magnetic field. These charged particles move along magnetic field lines, forming extended structures that connect polar regions. While this motion is dynamic and energetic, it does not produce widespread heating because the particle density is too low for efficient energy sharing. The thermosphere is also influenced by periodic variations in solar activity. During periods of increased solar output, such as solar maximum phases, more energetic radiation reaches Earth's upper atmosphere. This can temporarily increase particle energy and cause expansion of the atmospheric boundary. However, even during these periods, the fundamental limitation remains unchanged. The environment lacks sufficient matter to convert incoming energy into a stable warm medium. Heat transfer mechanisms that dominate lower atmospheric layers such as conduction and convection are largely absent here. Conduction requires frequent particle collisions, while convection requires a fluid dense enough to move as a coherent system. In the thermosphere, both processes are ineffective due to extreme rarity of matter. Radiation becomes the only meaningful method of energy exchange, but it primarily moves energy through rather than within the system. Satellites orbiting within this region experience a complex thermal environment. When exposed to sunlight, their surfaces can absorb significant energy, but in shadow, they radiate energy away into space. Because there is no surrounding dense medium to moderate these changes, temperature fluctuations can be extreme on individual objects, even though the surrounding space itself remains cold and sparse. Auroral activity occurs in parts of this layer, when energetic particles from the solar wind interact with Earth's magnetic field and upper atmosphere. These interactions produce visible light emissions as electrons collide with oxygen and nitrogen atoms. However, this phenomenon is localized and does not represent a general warming of the thermosphere. The energy involved is distributed across vast regions and remains insufficient to create a warm environment. The thermosphere gradually transitions into the exosphere, where particles become so sparse that they can escape into space entirely. This transition marks the final stage of Earth's atmospheric influence. Above this point, individual atoms follow ballistic trajectories influenced more by gravity and radiation pressure than by interactions with other particles. The concept of temperature becomes even less applicable as collisions nearly vanish. Despite receiving continuous energy input from the sun, the thermosphere remains effectively cold in terms of heat content. The reason lies in the extreme imbalance between energy input and matter density. Energy is abundant, but there is not enough material to store, distribute, or retain it in a meaningful way. The result is a region of high-energy particles embedded in a system that behaves thermally like near-empty space. This layer highlights a critical principle that applies throughout all regions of space. Temperature depends not only on energy, but on the ability of matter to interact and share that energy. Without sufficient density, even intense radiation cannot produce sustained warmth. Instead, energy remains scattered across individual particles, preventing the formation of a unified thermal environment. In this upper atmospheric boundary, Earth itself fades into space not by losing energy, but by losing the structure needed to hold that energy as heat. The thermosphere therefore serves as a bridge between planetary warmth and cosmic cold, where energetic processes exist without the density required to transform them into a continuous thermal state. Beyond the thermosphere lies a region where Earth's atmosphere no longer behaves as a continuous fluid, and instead becomes an extremely sparse collection of particles. This region is known as the exosphere, and it represents the outermost layer of planetary influence before true interplanetary space begins. In this environment, individual atoms and molecules are separated by distances so large that collisions are rare events, and many particles follow independent trajectories shaped more by gravity and radiation than by interaction with one another. The dominant constituents of the exosphere are light gases such as hydrogen and helium, along with traces of oxygen and nitrogen that have diffused upward from lower layers. These particles are not confined in a stable structure. Instead, they move along long curved paths, occasionally escaping entirely into space. Because interactions are so infrequent, the concept of a uniform temperature becomes increasingly difficult to define in a meaningful way. Each particle exists in a semi-independent energetic state. Solar radiation continues to play a central role in this region. Ultraviolet and extreme ultraviolet photons from the Sun can impart energy to individual atoms, increasing their velocity and sometimes providing enough momentum for escape. However, because the number of particles is extremely small, this energy does not accumulate into a warm or dense thermal environment. Instead, it is distributed across a vast volume, where it has little collective effect. The exosphere is also shaped by Earth's gravitational field, which still exerts a weak but persistent pull on particles. Lighter atoms, especially hydrogen, are more likely to reach escape velocity and drift into interplanetary space. Heavier atoms are more likely to remain temporarily bound before eventually undergoing similar processes. Over long timescales, this creates a gradual leakage of atmospheric material into space, reinforcing the extremely thin nature of the region. Energy transfer in this environment is dominated by radiation rather than particle collisions. With so few interactions occurring, conduction is effectively absent and convection cannot develop. Each particle responds individually to incoming radiation and gravitational forces, rather than participating in a collective thermal system. This isolation ensures that even when energy is present, it does not manifest as a sustained increase in environmental warmth. The transition from exosphere to interplanetary space is not marked by a clear boundary. Instead, there is a gradual blending of escaping atmospheric particles with the solar wind. At increasing distances from Earth, the influence of the planet's gravity weakens and particles become more influenced by the broader environment of the solar system. This overlap creates a region where planetary and solar particles coexist in extremely low densities. Despite being the outermost atmospheric layer, the exosphere still receives continuous energy input from both the Sun and Earth. Earth emits infrared radiation as it radiates heat absorbed from solar energy, while solar photons constantly stream through the region. However, the absence of dense matter prevents this energy from being retained. Photons pass through, and particles respond individually without forming a cohesive thermal structure. The behavior of particles in this region highlights the dominance of kinetic over thermal concepts. A particle may move rapidly due to energy absorption, but without surrounding matter to share that energy, its motion remains isolated. Temperature, which depends on large-scale statistical interactions, becomes less meaningful as a macroscopic descriptor of the environment. Occasional collisions do occur in the exosphere, but they are so infrequent that they do not establish equilibrium. When interactions happen, they are often brief and localized, with no lasting effect on the broader distribution of energy. This reinforces the fragmented nature of the region where physical processes operate on individual particles rather than collective systems. The exosphere also interacts with space weather phenomena, including variations in solar wind intensity. During periods of increased solar activity, more energetic particles can enter this region, temporarily increasing its energy content. However, the lack of density ensures that these effects remain diffuse and do not result in sustained warming. The energy is quickly dispersed into the surrounding space. This layer illustrates a critical transition point in understanding cosmic coldness. Even in proximity to a planet with a strong energy source and a well-developed atmosphere below the outermost region of that atmosphere cannot retain heat due to the breakdown of matter density. Energy exists, motion exists, but the structural conditions required for warmth no longer apply. As particles continue to escape into interplanetary space, the exosphere gradually merges with the broader solar environment. This process is continuous and ongoing, with no abrupt separation between planetary and interplanetary conditions. The defining feature remains consistent extreme sparsity of matter, prevents meaningful thermal coupling, ensuring that coldness dominates even where energy is constantly present. At the scale of the entire solar system, the distribution of energy becomes governed primarily by distance and geometric spreading, rather than by local accumulation. Radiation from the Sun expands outward in all directions, filling space with photons that carry energy across vast distances. This solar radiation is the dominant energy source within the inner solar system, yet its influence weakens steadily as it travels outward, not because it disappears, but because it is spread across an ever-increasing volume. The inverse square nature of radiation intensity means that as distance from the Sun doubles, the same amount of energy is distributed over 4 times the area. This geometric dilution reduces the energy density rapidly with distance. In practical terms, regions far from the Sun receive far less concentrated energy per unit area than those closer in. However, even in regions where solar radiation is present, the surrounding space remains cold because there is little matter available to absorb and retain that energy. Photons travel through the solar system largely unimpeded. In the absence of dense matter, they do not lose energy through frequent interactions. Instead, they continue their journey until they encounter a particle or object. This free-streaming nature of radiation ensures that energy is constantly moving through space, but not accumulating within it. As a result, the solar system is filled with energy in transit, rather than energy stored in a thermal medium. The outer regions of the solar system, including areas beyond the orbit of the outer planets, are dominated by extremely low-density gas and dust. This material is remnants of the early solar nebula interstellar medium and ongoing cometary activity. Despite spanning vast distances, this material is so sparse that collisions between particles are rare. Without collisions, energy transfer remains inefficient and temperature remains low in a macroscopic sense. Even objects exposed to sunlight in these regions do not contribute significantly to warming the surrounding space. While surfaces may heat up when illuminated, the heat does not spread into the vacuum because there is no surrounding medium to carry it. Instead, energy is radiated away again as infrared emission, continuing the cycle of energy movement without accumulation in the environment. The heliosphere plays a key role in shaping the energetic environment of the solar system. It acts as a bubble carved out by the solar wind within the surrounding interstellar medium. Within this bubble, solar particles dominate, but their density decreases with distance. Beyond its boundary, interstellar particles become more influential. However, both regions share a fundamental characteristic: extremely low matter density prevents efficient thermalization of energy. Occasional interactions between solar radiation and dust particles can lead to heating of those individual particles. However, the overall contribution of such interactions to the thermal state of the solar system is minimal. Each particle behaves independently, absorbing and emitting energy without forming a connected thermal system with others. This isolation ensures that heat remains localized rather than distributed. Cometary activity also introduces material into the outer solar system. As comets approach the Sun, they release gas and dust, creating extended tails that disperse into space. While these processes temporarily increase local density and energy exchange, the material quickly spreads out, returning to a diffuse state. The transient nature of these events prevents long-term changes in the overall coldness of the environment. The motion of dust grains and charged particles within the solar system is influenced by both gravity and electromagnetic forces. However, these forces do not directly translate into sustained heating. They guide trajectories and shape distributions, but without sufficient collisions, they do not create a warm or thermally uniform environment. The outer solar system thus represents a region where energy is abundant but structurally ineffective in producing warmth. The Sun continuously emits vast amounts of energy, yet the surrounding space remains cold because that energy is not retained by a dense medium. Instead, it passes through, interacts sporadically, and disperses over time. This layer reinforces a central principle: temperature is not determined by the presence of energy alone, but by the capacity of matter to interact with that energy in a sustained way. In the solar system, matter is too thinly distributed to meet this requirement on a large scale. As a result, even regions bathed in sunlight remain fundamentally cold in their physical structure. The solar system, when viewed as a whole, is therefore not a warm environment filled with heat, but a vast expanse where energy is in constant motion through a sparse and disconnected medium. This separation between energy flow and material density ensures that coldness remains the dominant condition, even in proximity to one of the most powerful energy sources in the local universe. As the exploration moves inward toward the fundamental relationship between energy and matter, the focus shifts to the physical mechanism by which sunlight spreads through space. Electromagnetic radiation, which includes visible light, infrared, and ultraviolet energy, carries energy through the vacuum without requiring a medium. This property allows the Sun's energy to travel across the solar system and beyond, yet it also explains why space itself does not become warm in the same way a dense atmosphere does. Light propagates as oscillating electric and magnetic fields that move through space at a constant speed. These fields do not rely on particles to carry them, which means they can travel through regions of near-perfect vacuum without losing structure. However, because they do not interact continuously with matter, their energy remains in transit rather than being stored locally. Only when photons encounter atoms or molecules can their energy be transferred into kinetic motion. In regions where matter is extremely sparse, such as interplanetary and interstellar space, photon interactions are rare. A photon emitted by the Sun may travel for millions or even billions of kilometers before encountering a particle. When such an interaction occurs, energy is transferred, but it is isolated and does not lead to widespread heating. The surrounding space remains unaffected because there are too few particles to distribute the energy further. The intensity of solar radiation decreases with distance due to geometric spreading. As photons move outward, they occupy a larger spherical volume. This reduces the number of photons passing through any given area, lowering the energy flux. Even though the total energy emitted by the Sun remains constant, its distribution becomes increasingly diffuse. This dilution is a key reason why outer regions of space remain cold despite continuous energy emission. Absorption of radiation depends heavily on material density and composition. Dense materials such as planetary surfaces or thick atmospheres can absorb and retain significant amounts of energy, converting it into heat. In contrast, sparse gas in space lacks the necessary structure to capture large quantities of radiation. Most photons pass through without interaction, carrying energy onward rather than depositing it locally. When absorption does occur in space, it often involves individual atoms or small dust grains. These particles may gain energy, temporarily increasing their motion or temperature. However, because they are isolated, they cannot easily transfer that energy to surrounding matter. They radiate energy back into space, often in different wavelengths, continuing the cycle of emission without creating a stable, warm environment. The concept of thermal equilibrium becomes increasingly limited in these conditions. Thermal equilibrium requires frequent interactions among particles so that energy is evenly distributed. In the vacuum of space, this condition is rarely met. Instead, energy exists in uneven and transient forms, constantly moving between radiation and isolated particles without settling into a uniform state. Even in regions close to intense energy sources such as the vicinity of stars, the surrounding space remains cold unless matter is sufficiently dense. This is because temperature is fundamentally a property of matter, not empty space. Without a medium to store energy in the form of particle motion, there is no sustained thermal state in the vacuum itself. The behavior of radiation also depends on wavelength. Higher energy photons such as ultraviolet and X-rays interact more strongly with matter when it is present, while lower energy photons pass through more easily. However, in low-density regions, even high-energy photons often travel vast distances without significant interaction. This reinforces the idea that energy presence does not automatically translate into heat. Over cosmic distances, radiation gradually loses effectiveness in heating sparse matter, due to both geometric dilution and the lack of interaction opportunities. Although energy continues to propagate through space, it does so in a form that is increasingly decoupled from matter. This separation between radiation and material structure is fundamental to the persistent coldness of the universe. This layer reveals that space is not cold because energy is absent, but because energy is rarely converted into a stored thermal state. Photons move continuously through the universe, but without sufficient matter to absorb and retain them, they fail to create a warm environment. The result is a cosmos filled with motion and radiation, yet dominated by thermal emptiness. The physical behavior of light ensures that energy is never stationary in space for long periods. It either continues traveling or is briefly absorbed and re-emitted by isolated particles. This constant movement prevents the formation of stable heat in regions lacking dense matter. Coldness therefore arises not from inactivity, but from the perpetual motion of energy without accumulation. At the deepest level of understanding, the relationship between temperature and matter becomes the central key to explaining why space remains cold despite the continuous presence of energy from the sun and countless other stars. Temperature is not a property of empty space itself, but a statistical measure of how particles share energy through constant interaction. Without sufficient matter, there is no stable system in which energy can accumulate, distribute, and reach equilibrium. This fundamental limitation defines the thermal character of the universe at its most basic scale. In dense environments such as solids, liquids, or thick gases, particles are closely packed and collide frequently. These collisions allow energy to spread evenly, creating a coherent thermal state that can be measured as temperature. In contrast, space contains regions where particles are separated by vast distances. In these conditions, collisions are rare and energy exchange becomes intermittent. Each particle carries its own independent energy state, preventing the formation of a unified thermal system. The absence of a connected particle network means that heat in the classical sense cannot exist in the vacuum of space. Energy can still be present in the form of radiation or isolated particle motion, but it does not manifest as warmth unless it is absorbed by matter. Even then, the effect remains localized, limited to the small number of particles or objects that interact with incoming energy. The surrounding space remains unaffected due to the lack of a medium capable of distributing that energy further. Radiation from stars fills the universe continuously, yet its influence depends entirely on interaction. Photons carry energy across immense distances, but they do not automatically raise the temperature of empty regions. Only when absorbed by matter can this energy be converted into kinetic motion. In most regions of space, such absorption is extremely rare, meaning that energy passes through rather than accumulating. The expansion of the universe further amplifies this effect. As space expands, matter becomes increasingly diluted, and radiation wavelengths stretch, reducing their energy density. This combination ensures that both the carriers of energy and the potential absorbers of energy become less effective over time. The result is a universe that trends toward lower interaction rates, and therefore lower effective temperatures on large scales. Even within galaxies where matter is more concentrated, vast regions remain effectively cold, because density is still insufficient to sustain uniform heat. Energy from stars, supernovae, and other energetic processes disperses quickly into surrounding space. Without continuous absorption and redistribution, this energy cannot maintain a warm environment beyond localized regions. The Sun itself illustrates this principle clearly. It emits enormous amounts of energy, yet most of space within the solar system remains cold, because the energy is spread across a vast volume with very little matter to absorb it. Planets and solid objects experience heating because they provide dense surfaces for absorption, but the surrounding vacuum does not retain this energy. It remains in motion, passing through or radiating away. At the most fundamental level, coldness in space is not an absence of energy, but an absence of structure capable of converting energy into thermal equilibrium. Energy exists everywhere in transit, but without sufficient matter, it cannot settle into a stable form. This distinction separates energetic activity from thermal experience, explaining why intense cosmic processes coexist with vast regions of extreme cold. The universe therefore operates as a system where energy is abundant but unevenly distributed and rarely retained. Matter provides the framework for thermalization, but it is sparse on cosmic scales. This scarcity ensures that most of space remains in a state where energy is present but thermally ineffective. Coldness emerges naturally from this imbalance between energy flow and material interaction. In this final inward layer, all previous regions converge on a single principle. From intergalactic voids to planetary boundaries, the same rule applies without sufficient matter. Density energy cannot be transformed into sustained heat. Space remains cold not because it lacks energy, but because it lacks the conditions required to make that energy behave as temperature. This understanding reveals a universe that is simultaneously energetic and cold, active and empty, radiant and thermally silent. The Sun's incredible heat and the countless stars beyond it illuminate space with continuous energy, yet the structure of the cosmos prevents that energy from becoming a widespread warm environment. Coldness in this sense is not a failure of energy, but a consequence of how space itself is built.